Good evening. My name is Mark Richards. I am the Dean for Mathematical and Physical Sciences at Berkeley, and it's my great pleasure to welcome you all to the 2008 Beverly and Raymond Sackler Lecture in the Department of Astronomy. My main duty is to introduce the introducer, but I will say just a few words about tonight's speaker. We are extremely pleased this evening to have a distinguished scientist, the former director of the Space Science Telescope Institute at Johns Hopkins University in Baltimore. There we go. That's too much. Dr. Steven Beckwith. And Dr. Beckwith is also just recently been named the Vice President for Research and Graduate Studies at the Office of the President for the University of California System. So he's also our boss. So it's a great pleasure to, particularly for the physical sciences and for the Department of Astronomy, to be able to host Dr. Beckwith for this special lecture and to welcome him to UC Berkeley and to the Department of Astronomy. I am not going to do the formal introduction, but I'll just make a few remarks, which is that Dr. Beckwith, as you will find out from Jeff Marcy, his academic pedigree and career has been mostly in private institutions. And so the change to Berkeley and to the UC system will be a change to a public institution, which, if you'll excuse the lack of gold-plated doorknobs, Steve, we do things a little bit differently around here. The University of California system hosts about 3 to 4 times as many students per faculty member as the institutions that you're accustomed to. And we're actually very proud of that in our role as a public institution. The Department of Astronomy here, by any measure, is in the top few departments of astronomy in the world, and certainly in the country. And if you hang around here very much, you find that probably between 1 in 4 and 1 in 6 of all students who come through as undergraduates in this institution take introductory astronomy from the likes of Alex Filipenko, or Jeff Marcy, or Elliot Quadrant, or Josh Bloom, or any number of our other stellar, if you'll excuse the pun, astronomers. Again, welcome to Berkeley. Welcome to the UC system, Stephen. This is primarily a welcome to the department. This is a tough crowd. This is kind of your interview. We hope it goes well. And without further ado, let me introduce another distinguished astronomer, Professor Jeff Marcy, who will do the formal introduction.
Thanks.
Well, it's a real pleasure to be welcoming Steve Beckwith here as our 2008 Sackler Lecture. I'd like to just say a few words about the Sackler Lecture. It's, of course, a delight for the astronomy department to be hosting these lectures that we do annually, our most prestigious lectureship. It, of course, is made possible by a generous donation from Beverly and Raymond Sackler, who make these talks possible, and do so, in fact, all over the world with similar Sackler lectures. Indeed, it's worth pointing out that philanthropic contributions like that of the Sacklers makes possible a lot of the astrophysics that we do here at Berkeley and elsewhere in the world, funding the largest telescopes in the world, funding the theoretical astrophysics that goes on as well. Tonight, we are indeed fortunate to have Dr. Beckwith here to give the 2008 Sackler Lecture. As Mark Richards just mentioned, Dr. Beckwith has just assumed the position of Vice President of Research in the entire UC system, overseeing the research from San Diego up to UC Davis. I'll tell you a little bit about his history, keeping it short. He was the director of the Space Telescope Science Institute until recently on the Johns Hopkins University campus, and he was also a professor there at Johns Hopkins University. When he was younger, he attended the engineering school at Cornell, where he did both engineering and physics, got his undergraduate degree in 1973, receiving a Bachelor of Science with distinction in engineering physics. And then from 73 to 78, he went to Caltech, where he did graduate work in physics and received his PhD in 78. He then joined the faculty at Cornell, where he taught courses there for 13 years as a professor. And of course, during that time, he won awards and held, at that era, many prestigious visiting positions at Arcetri in Florence. He had a short stint here at UC Berkeley, some others at Caltech. And then in 1991, he moved to Heidelberg, Germany, as one of the two directors of the Max Planck Institute for Astronomy, and later indeed became the managing director of the Max Planck Institute, where he was director from 94 to 98. He also ran several observatories from that position, the Calar Alto Observatory in Spain and several others. All that time, he was doing research as well, and his main research interests include the formation of stars and the early formation and evolution of planets around stars, especially planets outside our solar system. And more recently, he's been working fervently on the birth and evolution of galaxies, especially in the early universe, a topic that I think he'll address this evening. He's published over 200 research articles, and he's, of course, lecturing extensively to the general public and professional audiences. And he's won so many awards, I'm not actually going to list them, but I'll just mention that he is an elected member of the American Academy of Arts and Sciences, to which he was elected in 2004. So again, it's really a pleasure to have Steve Beckwith here in the UC system, and especially here at Berkeley for the 2008 Sackler Lecture. So let's give him a warm welcome.
Now I've got 3 microphones, so let's start, see if we can get it right. Can you hear me? Well, you probably can. Are the technicians ready? All right. Well, we'll try this. How's that? A little better? Okay, well, I guess I won't be able to walk around. I'm used to walking around. It's frankly a tremendous honor for me to be here. When I was given the opportunity to join the University of California system, yes, it is public, but it's without doubt the greatest and strongest university system in the world. There isn't any other system that has more than one flagship campus. I mean, we have many flagship. I know this is Berkeley. Okay, I understand that. But you actually have some competition now, and we noticed that in Oakland. When I went to Oakland, a lot of people thought I was crazy because you know, there's a lot of turmoil there, a new president and on that. And it is true. It's a time of it's a little chaotic, although it's a time of great opportunity. But finally, when people said, "Why did you go there?" I said, "Well, you know, it's just down the road from Berkeley." And that worked pretty well. That kind of shut them up. So I'm living in your reflected glory right now. And I will say one more thing about the talk. We may, in a minute, I'll ask you to lower the lights, because really I hope to show you some pictures that are going to be fascinating to you. And when the sun sets a little, that'll help too. But of course, this is an astronomy lecture. It wasn't, at least it doesn't seem to me that long ago when I was a student. And some of the things I'm going to talk about today were not even, you know, we just wouldn't even believed it. I see a lot of my colleagues in the audience who worked on this subject. I know High Spinrad, you know, you can remember back in the 70s. You know, I don't know about you, but I don't think we thought we were going to look back to when we actually could see the first galaxies being created. But we can do that now. Technology has advanced in a remarkable way. And a whole series of things have happened now so that we have a pretty good idea of how the universe was put together and where it came from. And this is a story you probably read about in the newspapers and you hear about, and you say, oh yeah, well, some scientists say that, but in fact, it's not too difficult to understand. Part of the reason for that has just been an explosion of technology that's given scientists the confidence to say we know what happened. But another part of it is we've got telescopes now that produce images that are so compelling that you, without training, can actually see, wow, yeah, that's really going on. And that's what I'm going to show you tonight. What I'm going to do is I'm going to take you on a little journey, sort of from the Big Bang until today. I'm going to concentrate a lot on when the first stuff was created, of which we're made of, the stars, the planets, you know, that sort of stuff. which happened in the first couple of billion years. I'll talk about the creation of structure, I'll talk about the creation of beauty, and I'll talk a little bit about why the future of this field is so exciting. I'm going to touch on many things that people on this faculty are actively doing right now and have made big contributions to. I'm not sure I'll be able to mention everyone's name, but it's going to be quite important. It was suggested that rather than speaking in clipped acronyms to my professional colleagues, that perhaps it would be useful to talk to a broader audience, that maybe you know generally what's going on, but would be helpful to be reminded of a few things. So the first third of this talk is going to be a kind of a tutorial. I'm going to remind you of all the things that you should know. For example, the age of the universe and why we know it, and how it expands and why it's accelerating and all that stuff. I'm going to do a little of that because it's a backdrop for what I'm going to talk about later. Then I'll tell a little story that started when I was the director of the Space Telescope Institute, which I don't know if it was obvious to everybody, but the purpose of the Institute is we actually ran the science program for the Hubble Space Telescope, which most people in this audience have probably heard of, and I'm going to show you the deepest picture of the universe and what it revealed. We actually can now look back to a time when the universe was different. So, if you didn't believe in the Big Bang before, I can show you a picture, say, well, go far enough back, it's different. And I think that's pretty profound. And then I'll talk about why, once we have this information, all the stuff that we can do to check that story. There are a few simple physics concepts that you need to know. No equations, well, maybe one, we'll see. But the one thing you need to know is that when you sit, especially in the back of the audience, you are actually seeing and hearing me a bit in the past, because it takes a little bit of time for the light from me to travel to you. Light travels a foot in a nanosecond. It's a great number to know, just in case you need it. So you're always delayed back in that back of the audience by, 40 or 50 nanoseconds. Now that's not a very big deal for my lectures. Okay, I'm not that fast. But when you look out into the cosmos, you have the same effect. So for example, if you go out on a dark night and train your binoculars on the Andromeda Nebula, M31, it's a galaxy. It's about 3 million light years away, roughly. So when you're looking at it, you're actually looking at it 3 million years ago. 3 million years isn't very long in our business. But we now can look back more than 13 billion years. And that turns out to be a very, very long time. And that's what this lecture is all about. So let me get started with my tutorial. It started, I'm going to try to walk and talk. Does the mic go away? Yeah. I'm going to take this stuff off. I feel like Clint Eastwood in the movie when he had all that stuff on. So I'll show you a few characters that involve. This is Edwin Hubble on the left. And what Hubble did, he did a lot of pretty good things. But the thing that he did, which was really profound, is he realized at one point when he was studying the spectra of galaxies that the galaxies he's looking at all seem to be moving away from us. It's a Doppler shift. So he looks at the spectra, and the spectra get a little shifted to red wavelengths, and that means they're moving away. It's the same basic principle that the police use to give you tickets on the freeway. But usually you're coming at them, not going away from them. Now, what he did then is he took measurements of all the galaxies, local galaxies he could get at, and he plotted them, and he found that this is velocity on the vertical axis and distance on the horizontal axis. The distance, incidentally, is in millions of parsecs. A parsec's about 3 light years. Think of it as a million light years. Since you don't know what a light year is anyway, it doesn't matter, but that kind of gets you oriented. And what he did is he found there was a linear relationship, that the further the galaxies were away, the faster they were moving away from us. Incidentally, this is a horrible data set. You'll notice there are no uncertainty bars. And this all turns out to be wrong. When done correctly, this was wrong. But he got it right. It turns out. So he said, well, gee, that means that the farther away you look, the faster these things are going. It's just like an explosion. If you look at the 4th of July, there's some of these great streamers that go out. When you have an explosion, if you take a snapshot in time a little later, the things that are twice as far from the center are moving twice as fast. They have to. They only had the same amount of time to get there, so they have to be moving twice as fast. So when he saw that, he says, it's just like the universe exploded from a thing, and now we're taking a snapshot. That's exactly what it is. That gave rise to the Big Bang theory. Okay? Now, somewhat later, groups did a better job of taking these data. By the way, I've shown, I don't know if you can see it. Maybe, could we maybe, well, that may not make a difference. You see this little orange thing right here? Yeah, that orange thing is twice as big as the size of the graph I showed you in the last one. So you really have to get farther out to do this right. But now you see that he got lucky, that in fact the universe is expanding exceedingly well in a, oh, thank you. Okay, that's great. In a very nice linear relationship. And it's just beautiful. Okay, so this really shows that the universe is expanding, that there is something, it's like we're in the middle of an explosion. And then that set off the course of modern cosmology for a while. Now, I'm going to jump ahead a little bit to show you one more thing. So this is this plot plotted again. Now I'm going to show you what happens if you go even further. It says 500 megaparsecs, that's 500 million, that's about 1,500 million light years. It's about 1.5 billion light years. Okay, so the stuff there, you're looking back 1.5 billion years. So let me plot this in a slightly different way. I'm going to take that down to a smaller amount. There's some data. And now I'm going to show you what happens when you pull this out and go much further. Incidentally, I've kind of switched on you. I've done a logarithmic scale here because I have to get way out. People said, okay, we need to test this all the way back. Let's see how far back we can go. And so they began taking data. And these two papers came out. Some of this is local talent. Saul Perlmutter is local here. Adam Rees is on the other coast. And you see the data don't really fall on that linear extrapolation of the line. I mean, you can actually just see this by eye, okay? And so that means when you look back in the past, the expansion was slower than this linear expansion, okay? And that was not expected at all, because if it was slower in the past, it means it's faster now. It means the universe is actually speeding up. I've shown you only one data set, incidentally, but this has been now reproduced many times with many data sets, and it really is true. The universe is not just expanding, it is expanding faster now than in the past. It's accelerating. It turns out that the stuff responsible for that is called dark energy. Why? Well, we can't see it. It must have some energetic features, and we don't know anything else about it. So we gave it a name, dark energy, and that's it. But that turns out to be about 65% of the energy density of the universe. In fact, it dominates the matter. That's the most important stuff. I'm going to return to this a little later. Here's a character. This is Fritz Zwicky. Fritz was an astronomer who I knew as a graduate student. He used to come to seminars, and he discovered many things in 1935, as I learned from him, that he never got any credit for. And he reminded almost every colloquium speaker with this exact expression that he should get credit for the major discoveries. Now, the biggest discovery, at least in my view, the biggest discovery he made that kind of goes down in history was the discovery of dark matter. And I'll show you how he did this, because it's very important for the rest of the talk. This is, take a guess, a cluster of galaxies. Why? Well, there are just a hell of a lot of galaxies in a very small place, okay? And we see these all over the place, and it's very clear if I were to zoom out. We'll get it right. If I were to zoom out, it's very clear that you'd see this very confined cluster. So what Fritz did is he said, well, if this cluster is confined, it can only be confined by gravity. There aren't any strings or bungee cords out there. So he could figure out how much gravity there is. And this is what he did. He started by saying, well, we can determine the mass that's in all the stars just by measuring the light. And then you have to sort of multiply by a mass to light ratio. But, you know, if it's like the sun, you know, you see a solar luminosity worth of stuff, it's a solar mass. Then he used these spectroscopic techniques that Hubble used to measure the kinetic energy of the galaxies as they were whizzing around. And then he applied this simple law that if they were bound, the kinetic energy must be about half the gravitational energy, so he could compare the two. And what he found was that the mass that was in gravity was about 50 times the mass in stars, in round numbers. And so it meant that for these clusters to be bound, and there were many of them, most of the matter in the clusters was stuff that you didn't see, okay? It was dark. And so it's called, help me, dark matter. Great, yeah, exactly. Because we have no idea what this stuff is, but we know we don't see it, and we know it's gravitating, so it must be matter. There are some ideas about this. The reason I bring these two things up is because the dark matter and the dark energy actually account for most of the stuff in the universe, and this really kind of dominates what we see. There are, let's see, there are more modern ways you can check this. Here's another way. Here's a cluster of galaxies, and you see all these little arcs here? Let's see if I've got a laser pointer. You see this here, and see all that stuff? Those are ordinary galaxies which are about twice as far away as the cluster, but they are all spread out because when you look through the cluster, you're looking through a gravitational well that acts just like a sort of a glass ball, just like a lens. And so all this cluster is doing is it's lensing the galaxies from behind through gravitational lensing. It's an effect that Einstein predicted, and we see clearly today in images like this from the Space Telescope. And because we know it's gravity doing this, it gives us a totally independent way of measuring the mass of the cluster and the gravity, besides these galaxy motions. And when we use that, we find the same ratio of light to dark matter. That is, the dark matter dominates. And so today, that was, let me go back. Well, it won't go back. So that says that we have this dark matter and dark energy, and in addition, that the universe is expanding. Now, the one final piece of the puzzle, and this is a little bit harder to get your arms around, but I'm going to try. The one final piece of the puzzle is that if the universe actually exploded from a Big Bang, and we run the clock backwards, there was a time when when all the stuff was together, when the universe was very hot. And if that's true, as the universe cooled, we expected that there was a time when that hot stuff cooled off and eventually emitted just enough light that it kind of permeated the universe. And that, in fact, happened. That's something called the cosmic background. And the biggest confirmation that the Big Bang theory was correct was when Arno Penzias and Robert Wilson, in, I think, 1961 or 62, or the early 60s, they discovered this background light, this background radiation, and that's the cosmic background itself. And here, you see in the cosmic background, it's very uniform on the sky. It has a very, very uniform temperature. It's about 3 degrees Kelvin. But if you subtract the average uniformity, which I'm going to do here, then it turns out you see this kind of a pattern on the sky. And that's because when you subtract the average, we're moving with respect to the cosmic soup. We're actually, the Earth and the solar system are moving with respect to the cosmic soup. That's what's called a dipole. You're moving toward it in the blue and away from it in the red. We're just moving, and so you see this pattern. Well, if we believe that, we can subtract that pattern, and that pattern leaves us with this. And what does that look like? Well, this is actually the Milky Way. Then once we've gotten rid of the average and then the first moment, and we get down to where the galaxy dominates. These are the stars and the gas and dust in the galaxies. And finally, if we subtract that, we get down to this. These are the small fluctuations in the background radiation that was emitted when the universe was very hot and emitted light at about 300,000 years age. There's a reason I'm showing you this. This looks a little esoteric, but the reason I'm showing you this is these fluctuations turn out to provide the seeds that later will become galaxies. And since what I'm going to talk about is the creation of galaxies, it's good to get your arms wrapped around the idea that at an early stage, the universe was pretty smooth, but not perfectly smooth. In fact, these fluctuations are just a few parts in a million of the average. But a few parts in the million was all it took to eventually give stars and galaxies and planets and us in this lecture you're hearing tonight. And so that's actually kind of profound. These are the two people who were given the most credit for this local confirmation. John Mather at Goddard Space Flight Center, George Smoot, who's at the Lawrence Berkeley Lab, and they both won the Nobel Prize for this just a few years ago. Okay, so here's our standard cosmology. And you keep this in mind, and then I'm going to show you a picture of the history of the universe, and we'll get to the galaxies. So most of the stuff in the universe is this dark energy, and the only thing we know about it is that it's creating the acceleration of the universe, but other than that, we don't have much of a clue. That's about 65%. Then another 30% is in dark matter. That we also don't see, but at least we have plausible physical theories for what it is. I won't go into that, but at least they're plausible. And then the last 5% is all of the stuff that we tend to find is interesting. In fact, the stars only account for 0.5%. I won't talk about these. We, the Earth, the heavy elements, all of us, we're like 0.03%. And I won't get into the biomass of humans on this planet. It's tiny, incidentally, compared to the number of bacteria that are living in the soil below us. we're pretty insignificant on this scale. But what's interesting is, although this is the stuff that we're interested and tend to study, this is the stuff that dominates. That's our current cosmology. Now, there are a couple of other things that come out of this. I won't discuss why. We believe we have a very precise age for the universe. We believe it's been 13.7 billion years, gigayears, since the Big Bang. We think we know that to 10%. We think that the Hubble expansion constant is 70 in standard units. This is the temperature of the cosmic background. So we know quite a bit, and we've had many ways to confirm this cosmological model. And so we really, really believe this is true. And I've actually shown you the three of the strongest underpinnings for why it's true. I showed you two examples of how you measure dark matter, very plausible. I've shown you an example of how you measure the expansion of the universe, very clear, and even the data for the acceleration of the universe, and that's pretty clear as well. So we know this pretty well, and there are many other pieces of the puzzle that I won't go into, but I want to do something a little different. So now, I talked about the density fluctuations in the early universe. Well, this turns out to be at a small scale. Well, let me just stop this for a minute, because it looks like one of these is hidden. Hold on. Right, okay. Let me start again. So these are the fluctuations that were measured with the COBE satellite in 1993, I believe, 1994. More recently, there was a new satellite called WMAP that measured with a finer scale. Now, you see the general patterns. I'm going to go back and forth. You see the general pattern is the same. You see there's that big hole in the center. There's sort of bright spots on the light. But now you see in this pattern, there's much finer detail. And when you look at this map, you can sort of see in this map the structure of the typical wave pattern. And you'll see what I mean by this in just a minute. But basically, there are some typical sizes in this map, just sort of like waves on an ocean, that will tell us exactly what the how the galaxies developed. Let me get you clued in. This is a picture of ocean waves. If you've ever looked at the ocean waves, you know it's very easy to see, even in a fairly chaotic sea that's blown by the wind, you tend to get swells which are of a certain length. This is very, very common. If you ever go, you all know about the swells. And the length of the swells changes with time, but basically there's a general swell size. So here I've shown at least one swell size, and that's about 5 meters across. If you look carefully at this picture, you'll see there's sort of another size of scale. It's about 1 meter. These aren't big swells, but you can definitely see that 1 meter pattern in this picture. And so now, if you were to take a spectrum to say, I want to plot the intensity of waves at different sizes, different wavelengths, you'd get something like this, where you'd say, well, at a scale of 1/5 meters, there's a big amplitude, that's the big swell, and then at a scale of 1/1 meter, there's another big amplitude, that's 1 meter, and in between there's a lot of noise. So you'd be able to see the characteristic size of these waves in an otherwise chaotic ocean. Just, because it was interesting, I went on the internet and I found some actual images and spectra of ocean waves, and this is the ocean, this is plotted in terms of time, that is the frequency the wave passes by, and this is direction. But you see here there are two peaks in these ocean waves, a low frequency, which is the swell, and a slightly higher frequency. So this is actually what the ocean looks like. And in fact, it's the information in these spectra in the cosmic background that tell you what the typical size scale of fluctuations of density in the early universe were. And those fluctuations in density grew to become the galaxies we see today. And the basic idea is shown here. If I take this picture, the cosmic background radiation fluctuations, and I take this power spectrum, as I said, so I measure the strength of waves at different scales, you can see this picture, which otherwise looks chaotic, has a remarkably regular structure where there's a peak in the power at about 1 degree. So about 1 degree angle on the sky, you get a lot of power, and then you get these other ripples. And it turns out this is precisely predicted by a theory of how the universe should look at the early times. And it's that kind of information that tells you exactly that the whole picture of the Big Bang is right. Here's that 1 degree scale. And it's very similar to what you would do in the ocean waves, which is why I make this. And it's really these things that are going to grow and become the seeds of later clusters and galaxies. I've got a movie to show you how this works. This is a simulation of the early universe. I apologize if you're not used to it. This refers to redshift. This is the universe starting at an age of about 100 million years old, and it's going to go up all the way to today to 13.7. And what you're going to see as I play this movie is the slight clumps. Well, you may not be able to see it very well because of the contrast. I'm afraid the contrast may do it. The slight clumps begin to clump up because as the universe ages, gravity begins to pull in matter where it's overdense, and it leaves voids where the matter is underdense. And in the end, after a long time, you wind up with a universe that has clusters of things, it has walls of things, it has voids in between things. This simulation shows us what the universe should look like as galaxies form out of these little fluctuations. Okay? That's the way that galaxies developed out of the little fluctuations. And it makes some very strong predictions about what the early universe should have looked like. Okay, that's enough for the tutorial. Let me just remind you, so this is a simple history of the universe. We started with the Big Bang. There was a radiation era when it recombined. You get this microwave background, which we measure. There was a long period, somewhere between a few 100 million and maybe a billion years, when we don't think there was much going on, and then the first galaxies, stars, and black holes began to form, and eventually clusters and groups of galaxies formed as the big stuff built up from the small stuff. This is our basic history of the universe. Now, until a few years ago, we could see this, and we could see this part, but we couldn't really connect anything in between, because the biggest telescopes we built were able to look out pretty far, but they weren't really able to look out far enough to the point where the universe looked any different. That changed when we put the first big telescope into space, the Hubble Space Telescope. With the Hubble Space Telescope, and at least equipped with modern cameras, it was possible for the first time to look out to a distance where we were getting back in time to where these first stars and galaxies formed. And so that's going to be the basis of the next part of the talk, which is what the universe looks like when it was very young. This is the Hubble Ultra Deep Field. I think it's a little hard to see. Maybe let's try diminishing that light and see if that helps. I don't know if it will because we've got a light from up there. I'll show you a little bit better in a minute. This is the deepest picture ever taken of the universe. It was taken by exposing the Hubble Space Telescope on an otherwise blank spot in the sky for 1 million seconds. In this picture, there are 10,000 galaxies in a spot on the sky that's smaller than if you held, you know, sort of a small pin out at the length of your arm and looked through that at the sky. Extrapolated to the whole sky, this says there are over 400 billion galaxies on the sky at the depth of the Hubble Deep Field, Ultra Deep Field. We knew this was going to be profound, and so when we scheduled the telescope, we made sure we did it in a biblical way. We started in September of 2003, and we exposed the image for 40 days and 40 nights, and then we rested. And then, after about a month of rest, in December of 2003, we picked up again and we exposed for another 40 days and 40 nights. And on January 16th of 2004, we stopped. And at that point, we had 1 million seconds of exposure, over 400 orbits of equivalent telescope time going into it. And we did it. It was really quite a day. It was an interesting day because on January 16th, we not only took the last image for the Hubble Ultra Deep Field, but that was the day that Sean O'Keefe, the administrator of NASA, announced to the world that we would no longer be servicing the Hubble Space Telescope, and therefore we would let it die. So we got it in just under the wire, I should say. Then there's a history associated with that involving, it's a little bit like Troy. In the end, all the kings and heroes died, but Hubble lives on, and so we've still got Hubble with us, and they're going to service it. But let me come back to this. One of the things about this image is it's so interesting. You can't see it on a screen like this, so I've got something that I can help you. You can try this at home if you want. So for those of you who have a fairly high bandwidth link in your house, if you go to this website, you'll find something called the UDF Skywalker. And the UDF Skywalker allows you to walk through this image. Yes, I know. Yes, I know. Let's see. And here's how it works. So in the upper left-hand part, you have this Hubble Ultra Deep Field with a green circle, and in the right-hand part, you then have a blow-up that shows you what the galaxies look like. And I'm just going to walk through this image and show you some of the things you see, because it's kind of interesting. Here's an obvious, clear set of galaxies, of clusters of galaxies. Now let me just say that you have to take away a couple of things from this image. The first thing is, you see this big red galaxy or orange galaxy in the center? That is an elliptical galaxy. About half the galaxies we see in the sky today are shaped like that. Very smooth, very regular, spheroidal, and rather red. That thing there is a star, by the way. Stars, for reasons I won't go into, always have these little spikes so you can tell they're stars. Okay? And for the astronomers in the crowd, that's a 20th magnitude star. So it's pretty bright on this scale. So those are the elliptical galaxies. Then the other half of the galaxies around are the spiral galaxies. Those look a little bit like the Milky Way. Here's a typical spiral galaxy. By the way, this spiral galaxy is far enough away that the universe was only 9 billion years old when the light from it left us. Looks just like the Milky Way. Those are the two types of galaxies we see. But as you scan through this image, you will see that the smallest and deepest galaxies, the ones at the edge of the universe, actually don't look anything like that. They look kind of like train wrecks. So you see the galaxy in the center there. You see that doesn't look like a spiral or elliptical. It's kind of chaotic. This galaxy in the center, that's also a sort of little conglomeration, not a spiral or elliptical. Quite different. There are sections of this image where you can see all of the galaxies are just chaotic. You see that? That is a galaxy that does not have what we call beauty. Only a mother could love this galaxy. Okay? This galaxy is clearly going to be an orphan in most universes. Okay? Why does this galaxy look this way? Why is this not a spiral or elliptical? Well, the reason is because we are actually looking back to a time before the universe had a chance to create any spiral or elliptical galaxies. What we are looking at are the little cusps of that movie I showed you, where the universe is beginning to clump up and build galaxies from scratch. And so the galaxies we're seeing in the early universe are smaller, they're less regular, and as I said, only a mother could love. Because in fact, these are just babies. These are real infants. And I'll show you two little things, and then I'm going to go back to the tutorial. So the galaxies that are most distant are very red for reasons that you'll see in a few minutes. Let's see if I can find one of my favorites in here. It's hard to navigate. Yeah, you see that little red one in the center? That's a galaxy that light was emitted when the universe was less than about 1 billion years old. Remember, today it's almost 14 billion, so that's a long, long time. Well, you know, I have a bunch of these in the talk, so let me just go back to the talk and we'll get it going. So here's the next part of it. So here what I've done is I've plotted a bunch of galaxies I've cut out from the picture that show what the universe looks like at different times. So you see up there is that spiral galaxy you saw down here, this spiral. That galaxy was emitting its light when the universe was about 9 billion years old. Okay? So the universe was already rather aged. If I go back to 3.3 billion years after the Big Bang, this is a typical galaxy. It's almost as large as this, but it just looks completely chaotic. It has not really been built up into this beautiful spiral galaxy. As I go back in time to 1.8 billion years, 1 billion years, and even 0.8 billion years, 800 million years after the Big Bang, galaxies get smaller, they get redder. Eventually, you're just looking at the little pieces that are going to build up and become the beautiful galaxies we see today. In this picture, we are actually looking back in time to a time when the universe looks different than it does today. These are typical galaxies at that age. These are typical galaxies today, and you can see the difference. So if you didn't really believe in the Big Bang, if you can believe that at least I know how far away these galaxies are, really, when you look out in this deep image, you're seeing the universe in a different light. One of my colleagues, Deborah Elmgreen, and her collaborators in 2005 went through the ultra-deep field and tried to pick out all sorts of different galaxy shapes they could classify. Here are the typical elliptical galaxies and the spiral galaxies you see today, but then there are all sorts of weird ones. Tadpole galaxies, double galaxies, something she calls clump cluster galaxies, and then these skinny things, which I picked up, called chain galaxies. You basically don't see many of these things today. I mean, every now and then you'll run across a rogue galaxy that looks like this, but you don't see many. But when you go deep enough in the sky, you see lots of them. In fact, you see none of these and lots of these. Because, in fact, we're looking back far enough in time that the whole nature of the galaxies is changing. All right, now, I mentioned that we could tell galaxy distances, and let me just give you a little idea of how we do that, because that'll figure into this part of the talk, too. If you look at the starlight from a galaxy, if you look at the spectrum of the galaxy, where this is some sort of intensity and this is the wavelength of light, visible light, incidentally, is between about 3,000 angstroms and about 7,000 or 6,000. So we see this. There's a strong edge in almost all galaxy spectra right at the edge where hydrogen becomes ionized, 912 angstroms. That's called the Lyman edge from Lyman, who discovered this in hydrogen. This is the spectrum of a typical galaxy. These are the pass bands of typical filters we use, such as the ones in the ultra-deep field. They're the blue band, the visible, infrared, and Z. I don't know why it's called Z, but that's just what it is. And these show how the filters are arranged. And that's how we make these color pictures, incidentally. We expose the electronic detectors in 4 different bands, and then we create a color picture from the 4 bands. As galaxies get to larger and larger distances, so this is a galaxy at a redshift of 1. This is when the universe was about half its present age, at about 8 billion years. The light is redshifted because the universe is expanding. And that means that this sharp edge goes to longer wavelengths. As galaxies go to very large distances, this is a redshift of 4, the universe was very young there, you see that this edge deepens and it moves into a band in such a way that, in fact, you don't get any more blue light from this galaxy. You only get light in the visible, infrared, and Z bands. And as it gets to higher wavelengths, you can see how this goes. And so here what I've done on the right is I've plotted a picture of a galaxy in 4 bands. And you can see that this band, you can see it in the Z band, and the I band, and the V band, but you don't really see it in the B band. This is a B dropout. This is a galaxy which is out at a redshift of about 4. So if I just compare the different filters in this image, without doing any other work, I can actually place these galaxies roughly in the distant universe. And you can see the galaxies that drop out of the I filter must be the most distant galaxies indeed. And in fact, they are. And I'll just show you in the next how this works in the next one. So here's the Hubble Ultra Deep Field again. And this is one of the galaxies in the center, one of my favorites. This is at a redshift of 5.8. And this is a spectrum we got of this galaxy with the Hubble telescope. Hubble has the ability to take spectra as well as take images, but it's much harder to do, so you can't take spectra of very many. This is the picture of the galaxy. You see it's a little red thing, and this is that Lyman edge. And I think it's unmistakable that this is the spectrum I showed you, right? But this Lyman edge is out at about 8,000 angstroms, which means that it's out, it's kind of 8 times or 8.5 times the actual wavelength of the rest wavelength of that edge. And so this is at a redshift that's pretty high. Okay? And that's how we identify redshifts. You can go through the Hubble Ultra Deep Field, and then you can just simply count galaxies in different slices of the universe. So, for example, these B dropouts, the things that aren't seen in the B filter, this is very typical. You see these 4? This is the one I showed you before. It's a very clear galaxy. You just don't see it in one of the filters, so it must be out at some redshift. In the Ultra Deep Field, we see about 504 of these. And in all of the associated fields that we've done with Hubble, we see almost 5,000 of them. We have a huge sample of these galaxies. And actually, this sample is very important for drawing general conclusions. This also works for the other bands. So this is one that drops out of the V band. You see it brightly in Z and I, but you don't see it, well, maybe a little bit in V, and it's gone by B. So those are at higher redshifts, and we see fewer of those, but we still see them. We see, in fact, 204 of them in the ultra-deep field and almost 1,500 of them in more extended fields that we've done since then. And finally, the most exotic and most distant are the I dropouts. Those are at the highest redshifts above 5.7. You can see this one is interesting because it's a combination of a B dropout. You see this complex you hardly see in the B band, and a Z dropout, which is right in the center of them. So even though these galaxies would look like they're all together, one of them is much farther away than the others. So you see, it's very critical that we have this technique for slicing so that we can actually get a three-dimensional picture of the universe at this time. Otherwise, just looking at these structures wouldn't tell us anything. But we have a tremendous amount of information from this, and that allows us to draw some general conclusions. So, for example, and in this case, there are 54 of these in the ultra-deep field and about 600 of them in all the other fields. So, for example, this is a plot of 24 of the brightest of the eye dropouts. That's the most distant galaxies you see. They're at redshifts greater than 7. That means that these galaxies emitted their light when the universe was less than 1 billion years old. And you see they have this small red chaotic structure. And just for comparison, I'm going to show you what the Milky Way would look like at the same distance. So this is the Milky Way at the same high redshift. And you see, none of these look anything like the Milky Way. Now, actually, I've had to make the Milky Way a little brighter because we couldn't quite see the Milky Way at this distance. But the structure is exactly the same. So you can see that the universe really did generally look different at those early times. Here's another way to look at it, because you might wonder about the structure. I know some of the astronomers in the audience will say, well, gee, Steve, you know, you're observing these in the rest frame ultraviolet. If you don't understand that, don't worry about it. But if so galaxies look different. Well, these are the 24 brightest B dropouts. These are at redshifts of about 4. And these are a series of galaxies that were observed in the ultraviolet, the same rest frame band with the GALAX satellite. And they've been redshifted, you know, as they would appear out at those redshifts. And I think you can see that the local galaxies and the distant galaxies really don't look very much like one another. And so really, when we do these slices, we're looking back in time in a very profound way. Now, here's something which is, and I apologize for the plot, but here's something which is also interesting to do. So another question you might ask is, well, I have this theory of buildup by clumping from the seeds, the density fluctuations of the early universe. That must tell me something about the distribution of small versus big galaxies. It may be harder to create big galaxies than small galaxies. That's generally the case. And so theoretically, you would expect that if you plotted these are bright galaxies. So this is the luminosity or the brightness of the Milky Way. This is 10 times the Milky Way, 1 times a 10th and a 100th. If you plotted the density of these galaxies, that is the number per cubic megaparsec, you would expect there to be many more small or faint galaxies than bright galaxies, because it's easy to form the small ones and it's harder to form the big ones. And indeed, that's exactly what you see. This is an example of that. But theoretically, you would not expect this galaxy set to turn over. You would expect this. In fact, most of the theories would predict a sort of a general power law. And so this actual shape is of interest to physicists and astronomers who are trying to understand whether or not the theories of structure development actually correspond to what we see in the data. And the hierarchical assembly idea predicts that you would have a general power law. Well, let me just show you what you do if you plot this for several different distributions. So in the ultra-deep field, you can see this is the redshift 4, 5, and 6. This is going back in time from about 2 billion years to less than 1 billion years. And you can see that from 2 to about 1.5, it doesn't change much. But now you begin to see evidence for a change. And in fact, a big part of astronomy over the next decade will be trying to measure these distributions very precisely in slices in time and comparing them with our theories to see if they make any sense. And in general, it looks like the energy density of galaxies does decrease. We're looking at galaxies in the past. They're much fainter than they were in the present day. This is the latest attempt by Richard Bouwens and his collaborators at the University of California, Santa Cruz, to measure even higher redshifts with the Spitzer satellite. And these are sort of preliminary results. So it shows you that so far as we can tell, we are looking back. The universe is getting, things are building up from these high redshifts early times to the low redshifts today. And what's also useful to point out is that this whole side of the curve, you may not be able to see it very well in the projector, but from about this line on over, all of these galaxies can only be seen with the sensitivity of the Hubble ultra-deep field. So while it's possible to see some of these deep galaxies by taking shorter exposures and using other telescopes, it's only with this sort of incredibly deep image with the world's most powerful telescope that you're able to get back to the point where we can measure the distribution of galaxies and actually compare them with our theories of how galaxies were created in the first place. And to a large extent, that's what motivated the ultra-deep field. We knew we would see back. We had already seen back some, but we really didn't have enough data to be able to say much about how the universe developed, and now we're getting to that point. This is a crude plot of the star formation history of the universe. This is today. These are redshifts, so this is back in time. This is billions of years after the Big Bang. The Big Bang is actually back here at a kind of infinity, but this is 1 billion years, 2, 3, 4, 5, 6, and this is 13 billion years after the Big Bang. And you can see that our best measures are that star formation, the rate of forming stars, started out low in the past It peaked at about 2 billion years after the Big Bang. So this really is the creation of most of the stars that we see in the universe. This period of the first 2 billion years did it, and then it dropped off very rapidly. This was the period in which you assembled the mass into galaxies, but those galaxies still weren't very regular. So that's the epoch of creation. That's the dawn of creation. This period is also interesting, and we're studying that today, also with ground-based telescopes, because this is where the beauty developed. This is when the universe actually had enough time to get rid of the chaotic motions and create the elliptical and those beautiful spiral galaxies that we see today. And so we can actually look back over a whole span from today back to less than 1 billion years after the Big Bang. Let me now talk a little bit about what will be done in the future, and then I'll wrap up. So you can get a flavor now for what you can do with some of these big telescopes, and you now get a flavor for how a lot of it fits together. So you might not have thought, for example, that the creation of galaxies had very much to do with the observations of the cosmic background radiation. But in fact, it has everything to do with it, because the fluctuations in the cosmic background radiation tell us what those seeds of galaxies were. And those fluctuations were created by imprints that had to do with the physics of the early universe. The physics of the early universe also should have imprinted that same kind of structure on the distributions of galaxies on the sky. Not just the cosmic background radiation, but also on the distributions of galaxies on the sky. So while we've mapped the cosmic background radiation, we haven't yet mapped the galaxy distribution. And this is the sort of thing that you would expect the galaxy distribution to be. Now, this is over the whole sky, but you can sort of recognize this. This is the end point of that movie I showed you of galaxies creating structures, clusters, walls, and voids in between. And you can see with your eye characteristic wavelengths here that if I took a spectrum of this, you would expect to see. Now, we don't yet know what the structure of galaxies on the sky looks like, not because we don't have the capability, but because it takes a lot of work. Literally, what we have to do now is we have to go out, and we can do this with small telescopes. We don't necessarily need Hubble. We don't need even Keck. We just need telescopes that will measure the positions and the distances to something like 1 billion galaxies distributed over the sky. And when we've done that, we can then look and see if this general prediction, at least in terms of the spectrum, is about what we expect. And there are two kinds of waves we'll look for. One are sort of the transverse waves on the sky, and the other are the longitudinal waves, the ones that go in and out. I couldn't draw it very well in this 2D picture, but in and out. Both of those give us separate information about how the universe developed and how gravity acted to create these great structures. This is sort of the expected wavelength. The standard wavelength is about 150 million parsecs, and that's what you see in these sort of structures here. That's about 150 million parsecs on the sky. These are the most preliminary measurements looking for that bump here. And the bump is this. And you see the data are not very good. I mean, they're sort of convincing there's a bump, but it's nothing like what you would expect from a beautiful experiment. These are predictions of what you could get. Very, very precise predictions. So really, just with some patience and outfitting standard telescopes with current technology, we should be able to test this, and that will be done over the next decade. And so I introduced you to this to show you just some of the things that will be coming up. It turns out that the development of structure, not surprisingly, depends very critically on exactly how the trade goes between gravity pulling things in and dark matter, which is accelerating the universe. Okay? Those two things are rather critical to that development. And so the prediction is that the way that structure develops in the universe is really intimately tied to our knowledge of both the way that gravity acts and the amount of stuff in the universe, both dark matter and dark energy. And so by measuring this structure that I showed you, this picture of the sky, and going back in time, not just locally, but to very high redshifts, and then comparing those slices, we can actually test whether our theories of gravity are correct, even back to the early times. So if you worried, for example, if you said, well, Steve, how do you know that physics is true out, at these early times? Maybe gravity was different. Well, you're right. Maybe it was. But the point is that it can be checked. And it can be checked in a fairly straightforward way with the kinds of tools and techniques I've told you about. Incidentally, this technique does have a name, and it's always good to come away from these lectures with a name so that you can impress your parents or your teachers or your children or whoever you want to impress. This is called baryonic acoustic oscillations. Okay, remember that, baryonic acoustic oscillations. It's really a good thing to know. So, for example, if you're a student and you go home for semester break and your father says, well, gee, Jennifer, what am I going to get for this, whatever it is, $20,000 a year or something I'm sending to the University of California? You say, baryonic acoustic oscillations. It'll just quiet the conversation, quiet the conversation. In fact, if you get this PowerPoint, you can impress them even more. So this is really a fairly exciting thing that will be coming up. Here's one other thing, and then I'm going to wrap up. We're getting to the end. The other thing, of course, is I've talked to you about the fact that by looking back in time, when we look back in time, we're looking at the universe that's expanding. And to do that right, you notice that as the galaxies get farther and farther back in time and farther out, the redshifts take the spectrum such that they increasingly become red. In fact, take it to the logical inclusion. It could redshift right out of Hubble's window. It can redshift right out of that Z-band at 9,000 angstroms and go out into the near infrared. And in fact, we see objects like this. So here is a picture of a galaxy cluster. And in the background of this cluster, there's an object which you can't see in the Hubble deep photograph. Okay? It just doesn't exist at Hubble. It's completely redshifted out of Hubble. But look, if you look at infrared light, because Hubble has an infrared camera, you see, well, lo and behold, there's an object. And if you look at longer wavelength infrared light, unfortunately, the resolution isn't good. It gets even brighter. So it is possible, if you go to infrared wavelengths, to go even farther back in time. And that's interesting because in the next servicing mission, which is really supposed to take place currently in October of 2008, keep tuned, we are going to I'm no longer part of that business. I'm part of you guys now. They are going to install a new camera on Hubble called the Wide Field Camera 3 that will have an infrared channel. And the current camera, which is called NICMOS, has this kind of a discovery efficiency or a discovery speed. This is as a measure of the sensitivity times the area of the detector. It shows you how rapidly you can discover new objects. And you see we're going to gain a factor of 20 with this new camera. Well, Hubble itself, without increasing the size of the telescope, just by putting new instrumentation, we're going to get 20 times the power in this telescope for the infrared. That means it will then be practical using Hubble to go out and look for these very high redshift galaxies in the infrared. And that's something that I think we can expect to see actually pretty soon because it's very exciting science. So this is the future. This gives you some clue as to what people are doing and why. There are a whole bunch of facilities on here. In a previous life, I used to sell telescopes, and I helped sell this one. The sample case got a little heavy, so I gave up, came here. This is the James Webb Space Telescope. Here's Hubble. This actually, incidentally, this background picture, this is a picture taken by a handheld camera by one of the astronauts on the space shuttle when they serviced Hubble last. And what they do is when they service Hubble and they let it go, they let it drift away slowly from the shuttle, and as it drifts away, they snap photographs with the Earth in the background, which I think is a very beautiful background. So this is Hubble. Hubble will be measuring the galaxy sizes, shapes, and luminosities all the way out to a redshift of 10, because that infrared camera will be able to extend its view even farther than we have. And it will be looking at the creation of beauty. That is, it will be looking at low redshift stuff as we're creating these beautiful spiral and elliptical galaxies from the detritus of the Big Bang, just grew out of these seeds of density fluctuations. The James Webb Space Telescope is a little bigger than Hubble, and it's cool, and it operates in the infrared. And it's really designed to be so sensitive it can actually take a complete census of galaxies between redshifts of 5 and all the way out to 20. If there are any galaxies, we think maybe there won't be. This should be able to really witness the dawn of creation. This will see galaxies turn on. It will be able to see galaxies at places where we think there are no galaxies. We'll run out. That's, sort of in this era. It's going to just push right back. It will also be able to see if there are enough galaxies to reionize the universe after these long dark ages. Here's a local project, the SNAP satellite, Supernova Acceleration Probe. Saul Perlmutter and Michael Levy are pushing this very strongly up a Lawrence Berkeley lab. If SNAP is launched, what it will do is it will measure the expansion history of the universe between a redshift of 0 and 2 very accurately by measuring thousands of these supernovae that were used to do the Hubble diagram. So rather than that kind of ratty diagram I showed you, by thousands of galaxies, you'll get a beautiful smooth curve. The idea of this is to go exactly from the imprecision of Hubble's first Hubble diagram to that first diagram I showed you by Reese Press and so forth. that showed a beautiful, beautiful linear relationship. And that we'll also be able to look at the dark matter as it evolves through time by looking at gravitational lensing. University of California is a partner in a project to build an enormous telescope called the TMT, the 30-meter telescope. And if that's built, it won't be quite this big, but, well, you get the idea. It will be able to collect enough light that even on the ground, it should be able then to take spectra of some of these distant galaxies and look at the dynamics of the assembly, so it'll see the velocities of the galaxies, as well as by looking at the composition of the galaxies and to see how the elements build up from scratch. Because the early universe was almost all hydrogen and helium. It was only stars and the galaxies that created the stuff we have today. The University of California also, through Davis, is a partner in the LSST, the Large Synoptic Survey Telescope. This telescope is a 6.5-meter telescope designed to take an entire survey of the sky every 3 days. Imagine the entire sky every 3 days. And by doing that, it will also catch every supernova out there, especially the local ones, and look for the expansion history. And then there are a bunch of things that you can do with smallish telescopes, wide field surveys, baryonic, acoustic oscillations, and evolving structure. Both of those things can be done. They're less expensive. They're just as interesting and sexy. And they all fit together in being able to test all along this line our hypothesis that the universe started from a very, very tiny point, hot point, by some mechanism we don't know, blew up and expanded and created all of the stuff that we see today. And you see, it's really kind of remarkable that all of this is coming together at this time. We are a long way from running out of ideas. Of course, ideas are, lots of researchers can have ideas. What's interesting is we're realizing these ideas. Even 3 decades ago, I could not have imagined as a student we'd really arrive at this point. I mean, and I'm not kidding. So I'm a bit of a romantic, but I still thought, forget it. I'd never bet anything on that. And yet we're at a point where we're literally getting far enough back that soon we will be able to test the theory of inflation in the quark soup by looking for polarization in the cosmic background radiation. Just wild, wild stuff. So I hope you pay attention. I hope you look at the pictures. The pictures coming out of James Webb will be like Hubble. You'll be able to see them. You'll be able to judge for them yourself. You'll even be able to kind of understand the science without too much effort. And so I'm very pleased that you invited me to talk to you. I really, this has been a love of my life, and I hope it becomes a love of yours. Thank you very much.
Thanks very much, Steve. A wonderful talk. We certainly have time for questions. If any of you have questions, feel free to go ahead and ask. Yeah, go ahead.
I think he was just stretching. About the size of the universe? Well, yeah, that's an interesting question. So the only thing we really know about the size is we can see out to a certain distance, which is called the event horizon. Maybe I should get the microphone. We can only see out to a distance which is the light travel time times the age of the universe. It's actually a little bit bigger than that for reasons I won't go into, but that's what we can see. That's our event horizon. We can't see beyond that. The universe could actually be infinite in size, and we would not be able to demonstrate that. But we do know it's finite in time. We do know that because it started at a finite time and expanded, it's a finite time, and that limits our horizon to a point where we can only see a certain amount of it. I can't see. Yes, in the front.
So there's all this dark matter, and you said you wouldn't go into why it's dark. I'm curious.
Why is it dark? Well, I'll tell you what the current theories are. So in fact, I can use this this little thing here. So in the early universe, what happened was prior to the time of the creation of the elements, the universe was so hot it was just elementary particles. I mean, really, really elementary. Electrons and other stuff. When it was hot enough, it created all sorts of exotic elementary particles, which we can see today in accelerators. We can create them. Most of them are short-lived. We believe, I mean, the most plausible theory is that there is a class of elementary particles which is much heavier than the typical protons, neutrons, electrons, the other fermions that we see today. A class of what's called supersymmetric particles, which are not easy for us to detect, but are gravitating, and they actually exist. And they were created at this early time. They kind of froze out. But because they don't interact very well with the rest of the matter, they're called weakly interacting. They just sort of sat there as stuff. And as the universe expanded, they're still there, and they gravitate, and that's what we believe makes up the dark matter. So they're very good, plausible theories from particle physics for what these are. I think the best is called the neutralino. I think the neutralino is the current favorite candidate. It is plausible that we'll be able to make some of those particles in the Large Hadron Collider, which is one of the reasons that people built it. And so it is plausible that's true. It's also plausible that with the right kind of laboratory experiments at places like Berkeley, we'll be able, the stuff's all over. I mean, it's pervading the universe, so it's whizzing around right now. Doesn't interact much. Don't worry about it. It's not like radon in your house, right? But this stuff is it's there. And so we do believe that with these sort of tabletop experiments, we might be able to find it. And that's why we think we at least have a handle on the dark matter theoretically. Dark energy, forget it. I mean, we have a number in an equation that we believe the number, but other than that, you might as well ask a 3-year-old and you'll get the same quality of answer for that. Yeah. Me too. Well, that's a complicated subject. It gets a little outside of my specialty, but basically today we see a lot of matter and not much antimatter. I mean, we know we can make antimatter in accelerators, but so the idea was that long time ago, matter and antimatter were created, but there was a slight imbalance in the matter and antimatter. There's a little more matter than antimatter, and at some point it all kind of recombined except for and turned it into photons except for the leftover matter. Now, why would this be true? Well, let's see if I can. How do you get asymmetries? If you have, let's say you have if you have a bowl and you put a ball in it, that ball will eventually roll to the center. That's very symmetric. Okay, I can create another symmetric bowl that has a hump in the middle. That if I put the ball in, it will never get to the center. It will go right up over the hump, but eventually it'll settle somewhere around that trough on the outside, sort of the donut part. That's a symmetric point, but it's not in the center. And so the idea was there was a potential. This is like a potential well. A potential that created particles, and this potential basically had a hump in the center. And then when all of the stuff kind of condensed out, it had to decide which way it was going. And it went to the matter side. I don't know if that's helpful to you. It helps me, but I think, that's the general idea of why there's more matter. And people who are smarter than I am can make me believe it. So, well, it's late. Oh, one more in the back. Yeah, please. Okay. Yes. Okay, so the question, let me repeat the question. The question is that I said that the star formation rate was highest, was at a peak at about 2 billion years. And the question is, why is that? Well, in broad terms, we think it's the following. At early times, the star formation rate was basically 0 because the universe had not had enough time for the gravity to pull stuff together. Then as the universe aged, pretty soon it got to that time where it was able to pull stuff together pretty rapidly. And that was in the first 2 billion years. And by 2 billion years, it was just going like gangbusters. Stuff was falling in, creating stars, and the clumps of stars were creating galaxies. But then as the universe expanded, eventually you exhausted a lot of that initial supply, and the universe got rare enough, underdense. That is, it expanded enough that most of the stuff that would have created the stars had already gone into stars, and you were beginning to exhaust the wells, and anyway, most of the stuff was getting farther and farther apart. So at that point, the rate of star formation on average went down. It was still high locally inside of some galaxies where they had captured a lot of matter that still hadn't made it into stars. But that stuff all damped down. And today, we see ongoing star formation. There's plenty in this galaxy. The sun's only 5 billion years old, so it had to have formed a little while ago and after the 2 billion year mark. But it's just not as much as it was in the past. And I think we always expected that anyway. So not only is this not a surprise, I actually worry that some of the observers are tilting their observations because this is what they expect to get. I kid you not. I have arguments with people about this. One more? Yeah.
Last question. So you suggested that really early times there's a possibility there of formation was taking place, that there were actual fundamental differences in the way that physics work, the way that sort of gravity works, the way that work, and non-astronomers don't know much about that. But what is, I suppose, what's the thinking about that? What would that imply about the sort of early creation period and also sort of our universe?
Let me see if I can just recapture that thought for the audience. So I didn't actually say that physics was different back then, but it might have been. I mean, it's a little hard if you don't go out and touch it and do experiments. So one of the problems, this whole scenario, this seems very seductive. I mean, all the observations fit, right? But it has a couple of nasty components. So one nasty component is this dark energy. I mean, what is this stuff? You know, it's just, we just gave it a label. But the problem is that people have started to think, well, you know what? I mean, this measurement of dark energy, say, and even dark matter, depends on gravity acting exactly the same way in the early universe as it did today. So rather than posit some fictitious dark matter, dark energy that we don't know anything about, why don't we just say that gravity was different in the early universe? Maybe that was the case. There's a guy who's worked on this for a long time, I think Morty Milgram, and actually every time he comes up with it, it still kind of fits the data pretty well. I mean, he's a pretty good physicist, so it's not completely crazy. But it's not the preferred solution. You know, I think most of us would prefer it if physics was the same, because otherwise it's hard to calculate anything. But my point was that by looking at the way that structure develops down here with time, by actually going back in time and looking at the way structure develops, we can distinguish between changing gravity and a substance which changes the way the universe is behaving. We can do that. And so it's a testable hypothesis. And that's why it's interesting, because it's testing something which is about as bizarre and exotic as you could imagine. But, you know, probably not more bizarre than quantum mechanics, say, or even general relativity. And those things we think are true. So it's always worthwhile to have these methods, because you don't know what the universe is like until you go out and discover it. And what's exciting is we have pretty good ideas now of how we could test some of these really exotic theories with tools that we have today. Thank you very much.
I think it's worth closing by mentioning one last thing, which is this eloquent talk by Steve Beckwith about the archaeology, if you will, of the universe, blowing away whatever the history professors here can tell us about, going back 13.5 billion years. A large fraction of it, frankly, was possible because people like Steve and Steve himself defended the major instruments, astronomical instruments and others in the United States and elsewhere, like the Hubble Space Telescope. Takes a lot of work to convince Congress, convince people at NASA, convince the American public that instruments like Hubble are really worth building. And I think the beauty of the universe that Steve Beckwith so eloquently described and the development of that beauty makes all of that work very well worth it. So let's thank Steve again for a fantastic talk.